The ring buffer, a queue that cannot allocate. This is data structures and algorithms, and this one is genuinely simple. It is an array and two integers.
Here is a real failure, and there's no bug in it. One thread writes timing samples into a queue. Another thread drains that queue to disk. In a quiet hour, the drain keeps up, and the process holds about 10 megabytes. Then traffic rises. The writer pulls ahead of the reader. The queue does not complain. It just gets longer. 3 million samples later, 2.25 million are still waiting, and the process is holding 617 megabytes. I measured that. It is a straight line, 200 megabytes for every million samples. Keep the line going, and you reach 2 gigabytes, and then the kernel picks a process to kill. Nothing raised, nothing logged, nothing got slower. So let us do the subject properly. This is about stacks and queues, and about the one whose size never changes. 3 things. First, which end do you touch? That single question is the whole difference between a stack and a queue. Second, an array and 2 integers, writing, reading, wrapping around, and how you tell full from empty. Third, and this is the real subject, what to do when it is full. Now 3 things this is not. It is not the stack and the heap. Those are regions of memory and a different video. It is not a message broker. There is no network here. And it is not a queue that grows. This one refuses to grow. Where does it bite? The kernel log you read with dmessage, where old lines vanish on purpose. Audio and video, where a late sample is worse than a missing one. And any window of recent metrics inside your own process. Before any code, one picture. On the left, a pile of paper in a tray. Every new sheet goes on top, and it always fits. The pile never tells you it is getting tall. The only limit is the ceiling of the room, and you meet that limit once, all at once. On the right, a wheel with exactly 8 pockets. One hand puts a card in, one hand takes a card out. The wheel turns, and the pockets come back around. There were always 8 pockets, and there always will be. Now ask each of them 3 questions. How much can you hold? The pile says, more. The wheel says, 8. How much are you holding right now? The pile has no idea. The wheel says, count them. What happens when you are full? The pile dies. The wheel says, that is your decision, not mine. One C-Python process on one machine. No broker, no network, no database. A request handler writes a timing sample, and a background thread drains those samples to disk. Capacity is 8, and that number is decided once, at startup, and never again. Then this line, which is the entire memory footprint of the buffer, a list with 8 places in it. Beside it, head, which counts how many samples have ever been written, and tail, which counts how many have ever been read. Both start at 0, and both only ever go up. One sample is one small dictionary, made by the request that produced it. That is the whole system. Everything in this video happens inside this one process, before any queue library exists. One level below that. A stack and a queue are 2 answers to one question. Which end do you touch? A stack has one opening. You put things on the top and you take them off the top. So the last thing you put in is the first thing you get back. That is what last in, first out means, spelled out. Undo history works that way. So does the call stack your program runs on. A queue has 2 ends, and they do different jobs. You put things in at one end and take them out at the other, like people at a counter. So the first thing in is the first thing out. That is a promise about order. Work waiting to be done. Events waiting to be written. Now, the mechanism, and there is no second half to it. At the start, head is 0 and tail is 0. They are equal, so the buffer is empty. Nothing has been written and nothing is waiting. A sample arrives, 41. We put it in the slot at head modulo 8, which is slot 0, and then we add 1 to head. That is a write, the whole thing. Another sample, 38. Head modulo 8 is now 1, so it goes into slot 1, and head becomes 2. Nothing moved. The list did not change size. A third one, and now the count is head minus tail, which is 3. 3 samples are waiting. Now the reader wakes up. It takes the value at tail modulo 8, which is slot 0, gets 41, and adds 1 to tail. It reads again and gets 38. And look carefully at slot 0. 41 is still sitting there. Nothing was erased. Only the cursor moved. That is all of it, in code. A list of n places, allocated once and never again. Head, the total number of writes ever. Tail, the total number of reads ever.
To push, you write into buffer at head modulo n and then add 1 to head. 2 lines. To pop, you read the value at tail modulo n, add 1 to tail, and hand the value back. Now look at what is missing from this class. There is no append. There is no resize. Nothing is shifted along to make room. There is no lock, and there is no loop. The list never changes its length, which means this buffer can never go and ask the operating system for more memory. Not under load, not at 3 in the morning, not ever.
Keep turning it. Head is 6, tail is 3, so 3 samples are live in slots 3, 4, and 5. Another sample arrives. Head modulo 8 is 6, so it lands in slot 6, and head becomes 7. Another one goes into slot 7, and head becomes 8, but the array has no slot 8. This is the only clever moment in the whole subject, and it is not very clever. 8 modulo 8 is 0, so the next write goes back to slot 0, on top of the value that used to live there, and head becomes 9. 2 more writes, and head is 11. 11 modulo 8 is 3. Notice what did not happen. The counter did not wrap. The counter is still climbing. Only the index wrapped. 1 modulo turned a straight array into a circle.
Which brings us to the one place a ring buffer bites people. 2 tests that look almost the same. With counters that only go up, empty is head equals tail. Full is head minus tail equals 8. The count is head minus tail at any moment. Those 2 tests can never both be true because the counters carry their own history. Now here is the version most people actually write, where head and tail are already wrapped down to 0 through 7. Empty is head equals tail, and full is also head equals tail. The same 2 integers with 2 opposite meanings. I measured this. A completely full ring and a completely empty ring produce the identical pair of numbers. This is the classic off by 1, and it is not a typo. It is a design choice you made when you threw the history away.
So if you did wrap your indices, how do you get out? There are exactly 2 ways, and the reason there are 2 is arithmetic. Either add 1 bit of information or delete one of the states. Adding information means keeping a third thing, a count, or a flag that says full, or the climbing counters we have been drawing all along. Those are not 3 tricks. They are 1 trick, 3 ways. Deleting a state means never letting the right cursor catch the read cursor from behind. Full becomes the slot after head is tail. You own 8 slots, and you can use 7. A buffer of 8 has 9 possible fill levels, and a pair of wrapped indices can only tell 8 of them apart.
And now the part that is not really a data structure at all. The array is full. A new sample arrives. Something has to give, and the data structure has no opinion about which. You can overwrite the oldest thing and lose old data, or you can refuse the write and slow the producer down instead. Same structure, opposite promise, 1 branch of code apart. This is a product decision wearing a data structure costume. Policy 1. Head minus tail is 8, so every slot holds something nobody has read yet. A 9th sample arrives. Head modulo 8 is 0, so it wants slot 0. But slot 0 still holds 41, and nobody has read it. Under this policy, we let it go. We add 1 to tail, which gives up the oldest sample. We write the new value into slot 0. We add 1 to head, and we add 1 to a counter called dropped. Then it keeps going, and the important thing is that the write never fails. The producer is never blocked and never told anything. What you lost is a number you can read. This is right when the newest data is worth more than the oldest. A kernel log, a window of recent metrics, a live audio stream. A sample from 4 minutes ago stopped being useful 4 minutes ago. Policy 2. On the same full buffer. Same array, same 2 integers, same moment. This time the write is refused. Push returns false. Nothing was written and nothing was lost. The producer now knows immediately that it is going faster than the system behind it, and it has to decide what to do. Wait, retry, or complain loudly. Then the reader drains 1 sample, and there is room for exactly 1 write. Now the new value fits. The producer waited, and the work survived. This is right when every item is work somebody is owed, a job to run, an order to fulfill, a payment to settle. Refusing is not the failure here. Refusing is the point, because it pushes the problem back to the one place that can actually decide what to do about it. Here are both policies in the same class, so you can see how small the difference is. The overwrite version asks 1 question. Is head minus tail equal to n? If it is, it adds 1 to tail. giving up the oldest, and adds 1 to the dropped counter. Then it writes, exactly as before, and returns true every single time. The refusing version asks the same question. If the answer is yes, it counts the refusal and returns false. It never touches the buffer. That is the whole difference. One branch. One returns true always and counts what it threw away. The other can return false and has nothing to count because it never lost anything.
Both of those were measured with 3 million samples, 1 writer and 1 reader. The growing queue put on 607 megabytes. The ring buffer, doing the same work, put on 0.64 megabytes, 949 times less. But the third number is the one that matters. The size of the ring array before and after was the same number to the byte. And here is the honest part. Python was still allocating, because every sample is still a dictionary. What the ring buffer removes is not allocation. It is the part of your memory use that has no ceiling.
So why would anybody agree to lose data on purpose? Because of what the other option actually costs. The growing queue never told you it was in trouble. It just took a little more memory, and then a little more, until there was none left. The ring buffer cannot take more memory. The only thing it can do is lose data, and it tells you exactly how much. That is the whole trade. An invisible risk with no number on it becomes a visible one you can put on a dashboard. A queue that cannot allocate is a queue that cannot surprise you at 3 in the morning.
Now, the costs. Honestly, because there are 3. First, you have to pick the size before you know anything. Too small and you drop all day. Too big and you paid for memory you never use. That number is always a guess. Second, the wraparound arithmetic is exactly where the off by 1 bugs live. Full and empty are 1 integer apart, and the test that tells them apart is easy to write backwards. Third, it is beautifully simple for 1 writer and 1 reader. Add a second writer and you need a lock, and a lock is not free. Measured here, a bounded queue with a lock costs about 33 times a bare append. 3 things this video did not cover: message brokers, how a deque grows, and lock-free programming. A ring buffer does not remove your problem. It moves the problem to a time when you are awake.
In practice, you will not write that class. Both policies are already in the standard library, and they behave differently on purpose. A deque with a maximum length gives you policy 1. Append to a full one, and it silently drops from the other end. The 1 is simply gone. Nothing raised, nothing logged, no return value to check. A queue with a maximum size gives you policy 2. Put into a full one without waiting, and it raises. And do not hand-write the class from earlier. Measured on this machine, 1 deque append costs 37 nanoseconds, and my hand-rolled push costs 285, because the interpreter charges for the method call. Write it out once to understand it, then use the 1 in the box.
This is not a teaching example. Every number here I read off the machine I am recording on. The kernel log is a ring of 256 kilobytes, fixed when the kernel was built, and when it fills, the oldest lines are overwritten and gone. Your sound card reads from a fixed ring, while your program writes into it, and if you miss your slot, you get a click, not a delay. The kernel profiler here is capped at 516 kilobytes per user, and the pipe between 2 commands is a ring of 65,536 bytes. I filled it, and it took exactly that many, and then it stopped and made the writer wait rather than lose a byte. 3 of those overwrite. 1 refuses. That is the same decision you just watched.
If this comes up in an interview, 3 questions. Why throw data away on purpose? Because the alternative is throwing the process away. Old telemetry is worth less than a running service, and the loss is counted so you can see it. For a job queue, the answer flips. Refuse instead. How do you tell full from empty? With counters that only go up, empty is head equals tail, and full is head minus tail equals n. With wrapped indices, both states look identical, so you add a bit of information or you give up 1 slot. Is a ring buffer threat safe? For 1 writer and 1 reader, it can be, because each side only advances its own cursor. Beyond that, you need a lock, and in Python, relying on the interpreter lock is not a design.
So the whole thing as 1 chain, an array and 2 integers, buffer at head modulo n equals x, nothing shifted, nothing allocated, which means the size is decided once at startup and does not move again under any load. So when it fills, something has to give.
overwrite the oldest, or refuse the right, one branch apart, and that costs you a guess at the size. Too small and you drop all day, too big and you paid for nothing, which buys you the thing worth having, a failure that is bounded, visible, and chosen by you instead of by the kernel. The habit under all of it, every Q you write should have a limit and a written decision for what happens at that limit.
Thanks for watching. If that cleared something up, hit like and subscribe so the next one finds you.